So today I'm going to talk, yesterday I talked about spaces, cell structures on spaces, CW complexes, and how you can reduce the number of cells. Today I want to use that technology in building classifying spaces for groups. But before I do that, there were a couple of questions after yesterday's lecture that I didn't answer too well, so let me answer them now. So, somebody asked me, my last slide was about the Cullen simplicial complex. Why are group theorists interested in it? Well, an answer to that is probably Cullen's result, which goes back to 1978, that if G is a non-trivial normal, if G has a non-trivial normal P subgroup, then, oh no, sorry, then the Cullen complex is contractible, and there's a difficult conjecture which that the converse may be true. I think I have to have difficulty with this. Can you hear me when I talk? Like that is okay, is it? Oh yeah, okay, so I don't hear it from here, fine, okay. So I was also asked, is this Cullen complex always a wedge of spheres? So to answer this, let me say that certainly if G is soluble, and if P is not equal to 2, then the Cullen complex is a wedge of spheres. But I had to look up the internet last night to find an example, the first example of a case where the Cullen complex is not a wedge of spheres. Take the symmetric group on 13 points and the prime 3, P equal to 3, then the Cullen complex isn't a wedge of spheres. And just before going to bed last night, I wondered whether you could get a smaller example. I haven't found a smaller example, but in fact, if you run these discrete vector field techniques on the symmetric group on 10 points, you find that the Cullen complex is homotopy equivalent to a wedge of circles and a two-dimensional complex. The two-dimensional complex has 53 one cells, 872 two cells, it's two-dimensional. It has a non-abelian fundamental group, and its abelianization is free abelian of rank 42. So I may ask somebody for help. I suspect that group is actually not free. So I wonder whether that's an even smaller example. But that's not what I want to talk about today. Today I want to talk about calculating the cohomology of a discrete group. So G throughout then is a group. And EG, I'll use EG to denote a CW space which is contractible and which admits an action of G, a free action. So the action must have no fixed points other than the identity. So I had this slide yesterday, which I think I was a little bit confused about. So let me look at this slide again. If you take G to be the group on two generators AB with this relation, and if you take EG to be the plane, and I got this wrong yesterday, so let me just, the x-axis is where my pointer is moving now, and so B moves up 1 unit, and A reflects in the x-axis, so then I think you do get that if you do A, that's the same as doing move up 1, cross and reflect, and then move up 1. So that's the group, that's the action. And then yes, well, the quotient of the plane by that action is the Klein bottle. And if you put a CW structure on the Klein bottle, you can use the techniques from yesterday to calculate the homology of that group. The question is, how do you actually put a CW structure on the plane or on the Klein bottle? I've cheated here a little bit because I just kind of pulled one from my hat, these squares. In practice, your group G may be given, for example, as a matrix group or as a group of affine transformations. So you may be given two affine transformations. And you know that those affine transformations act on the plane. You know that the plane is contractible. But in order to calculate the homology or the cohomology, you have to impose a cell structure on the plane. So there are several ways to do this. And one fairly generic way that works quite well is to do the following. Choose an arbitrary point V in the plane, any point. And then take the orbit of V under the action of G. This is an infinite orbit, but still you can do it. And then you build fields where you take, you put a fence around V, all of those points closer to V than to any other point in the orbit is the field containing V. You build a fence around it. And that kind of tessellates the plane. That's called a Dirichlet or a Voronoi tessellation. So let's just see, what does it involve? So you pick some point. I've chosen the point in red, and I've taken the orbit of that point under the action of G. So now I'm going to pick a second point, and I certainly want this Dirichlet Voronoi domain. It's got to consist of points which are closer to that red point than to this second one. So I kind of have an inequality. I have a half space. But the Dirichlet Voronoi region, also the points in it, they have to be closer to the original red point than to that point there. No, than to this point here, this point here. So I have another half space equation. And so that I know that my Dirichlet Voronoi region has to lie somewhere in this region. And then I take another point, which I call it here, and I get an intersection of half spaces. So you can actually build your Voronoi region as an intersection of half spaces, and that's just linear programming. So there's not a lot to do there. You can use off-the-shelf software such as Polymake and so on. So you end up, okay, there are infinitely many points to worry about, but it doesn't take a lot to convince yourself that you actually only have to deal with a finite number of intersections because so many points are far away. And in that way, you can build from your space a tessellation on which the group G acts, and it preserves the cells. And then we do what I was talking about yesterday. You take the cellular chain complex of your CW space. EG now is the plane. So these cellular groups, they are the free abelian group on the, this is the free abelian group on the two-dimensional cells. So there's one generator for every two-dimensional square there. There's one generator for every one-dimensional edge, and so on. And you've got this action of G, so you can actually interpret, the action happens to be free in this case, so you can interpret this free abelian group just as the group ring, because G acts freely on the two cells. And what I'm really saying is there's one orbit of two cells. Any one cell can be moved to another. There are actually two orbits of one cells. Any horizontal cell with this action can be moved to any other horizontal cell, and any vertical cell can be moved to any other vertical cell. You have two orbits of one cells, so you interpret this free abelian group as this group ring, and there's one orbit of vertices. So you end up with a chain complex, and then you want the cohomology, so you build, well, here I guess it's a co-chain complex. You take your favorite module, M, and then you look at the G equivariant homomorphisms from the chain groups to M to build a chain complex, and then the cohomology that you want to calculate is just the cohomology of that co-chain complex, and you can perform that in this case. For example, you'll find that the second cohomology with coefficients in Z is Z02. So there's a calculation starting from a pair of generators of a group that you happen to have, in this case, the fact that it acts on a contractible space, namely the plane. And I'm just going to repeat myself because I think this is the message I'd like to get across, if nothing else. Constructions such as homomorphisms, Thienemann operations, Hecker operators, they all apparently involve some kind of choice, but that choice can be made, well, they all rely even in the books on the fact that certain complexes are exact or certain spaces are contractible, and we want to record on the computer that a space is contractible, so the way we can do it is using the arrows from yesterday, and these arrows will play a part, not so much in calculating the cohomology, but when you want to implement operations on the cohomology, you will need these arrows for that. And then in GAP, there'll be, on my problem sheet, I've put some exercises involving resolution. So just to say quickly, what GAP stores in a resolution for a group G well, it only stores so many terms, so many of the chain groups up to a certain degree n. It stores the ZG rank of each free ZG module in the resolution. It stores for each orbit of cells, so for each orbit representative of cells, it stores a record of what's the image of a cell, so what's the boundary of a cell. And it also stores these arrows, and these arrows are stored, these arrows are not G equivariant, so you have to store, unfortunately, somehow, for every free abelian group generator, you have to store the image of the arrow, so that's kind of a homomorphism. Okay, so there was an example. I took the Klein-Bottle group, but that in principle works for any crystallographic group, because crystallographic groups Euclidean crystallographic groups act on Rn. Well, I'm jumping ahead of myself a bit. It works for any crystallographic group for which you have a fixed point free action. You can do that Voronoi trick, and that is implemented in GAP. And I should mention that the trick was you'd have your group G, which you know acts freely on Rn or on whatever the space. You take a vector V, you take the orbit of V. So you can ask, what happens if you take a different vector V? Could you possibly get a different tessellation? And sure, you can get a different tessellation, not so much with the Klein-Bottle group, but here's a group, crystallographic group, which is known to act fixed point freely on three-dimensional space. It's a three-dimensional crystallographic group, so it acts on R3. This is stored in GAP as space group number 165, and you can use polymake software to choose the starting vector V, then construct the fundamental domain. And then I have a picture, which isn't really mathematics. This is experimental art or something. It's what we did was for many, so we couldn't do all points in the plane. So for many points in, well, the first thing to say is that this particular group, the z-axis doesn't seem to have any effect on the fundamental domain that you get. So we can restrict to a plane, it's the xy plane, and then for every value of xy, or at least we digitized it, we took V and recorded the combinatorial type of the fundamental domain and gave a color. And there are actually 10 colors in that picture, but I was looking at it this morning, I can only see about 6. But somewhere there are 10 colors there, because there are 10 different types of fundamental, depending on where you take your starting vector. And here's one of the fundamental domains. So for example, that's one of the types, that tessellates R3 for that particular. But the resolution you get, number of cells, actually depends on the starting point, V. Let's talk briefly about finite groups, because you can do exactly the same trick for finite groups. Suppose you have a real representation, a matrix representation of your finite group G. Then G acts on Rn. So again, you can take a vector in Rn. You can take the orbit of the vector under the action of G. That'll be a finite set. And this time, I suppose, rather than taking the Dirichlet domain, you can just take the convex hull, the smallest convex set containing your orbit points. And the group acts on that combinatorial structure. So here's an example. If you take A4 and you take the permutation representation, the orbit there, I guess, has 12 points, so it acts freely on the vertices. P then is the convex hull of the orbit, and it's a nice polytope. And your group G acts on that polytope, and that polytope is contractible to a point. If you change V, so 4 goes to 1, you get a different polytope. So again, it depends on and I don't have a picture in this case for all the different possible polytopes. So you've got your polytope for the finite case. It's naturally a CW structure, it's naturally a cell complex. The group G acts on it, so the chain complex is a ZG resolution, but it's not free. And it's a little bit unfortunate in that the top dimensional cell of the polytope gets sent to itself by every element of G. So unfortunately, G stabilizes the top dimensional cell, which is a bit unfortunate. But if you remove the top dimensional cell, you end up with a sphere, the tessellation of the sphere, and G acts on the sphere. And if you do things properly, every cell will have a stabilizer group, which is a proper subgroup of G. So you can kind of work by induction currents. So that's just to record the fact that in the case of polytopes, typically the cellular chain group won't be free. It'll be a non-free module. One summand for every orbit of cells in dimension K. And so I'm assuming that my polytope is maybe m-dimensional. So if I omit the mth dimensional cell, I have the chain complex of a sphere. The chain complex of a sphere will have homology. The zeroth homology is Z. The top dimensional homology is Z. And every other homology is trivial. So except for top and bottom, I'm exact. So what you can do is you can splice things together to get well, in this case, it'll be a chain complex of infinite length. The splicing together means that this infinitely long chain complex, which is periodic, has trivial homology everywhere. You have to be careful about signs. There's a plus or minus one coming into that, but I won't go into that level of detail. So you can end up with a non-free resolution. It's non-free, but the stabilizer groups are all proper subgroups, so you could hope to work recursively. Or if you're lucky, you might come up with a group that actually acts freely. So let's take a group of order 8, the quaternions, represented as a group of 4x4 matrices, or real matrices, or 2x2 complex matrices. So that group acts on R4. And if you take a starting point and use polymake to calculate the orbit, you get a 4-dimensional polytope, which is a bit hard to represent. I've just shown the one skeleton there. And you do some checks, and you find that G acts freely on all of the cells. Each cell stabilizer is trivial. And so when you get this infinitely long periodic resolution, that is actually a free ZG resolution for the quaternion group of order 8, and from which you can calculate the cohomology. And you also see that the periodicity of the resolution means that the cohomology or homology is also periodic. And just briefly, I'll mention that, I mean, you really are dealing with topological spaces. So in Heiko's lectures, he's talking about presentations. One way of thinking of a presentation is that it's a 2-dimensional CW space with just one zero cell. So in principle, whenever you have a CW space, you can extract what's the presentation. And it's kind of intriguing that the computer gives this very classical presentation for this group. Yeah, so that comes for free just from the geometry. So let me do something else. Let me take a group that's known not to act on a sphere. Still a small group, because I can do the example. So the group of the symmetric group S3 of order 6 is known not to act on a sphere. So let's see, what would you do then? You'll have to have a different technique. Maybe get some, sorry? That's right, for it to act on a sphere, yeah, and this doesn't. On the other hand, it does actually have a periodic resolution. I'm not going to construct the periodic resolution, but I'm going to do something very kind of naive and number crunching. I'd like to construct then a resolution for this small group of order 6. So what that means is I have to construct a CW space X, which is contractible, and on which G acts freely. Well, I don't have any space to start with, so I have to build the space from nothing. It's going to be a CW space, so I have to have 0 cells, and I'll throw in as few 0 cells as possible. I have to have 1 0 cell, but the group G has to act on the 0 cells freely, so I have to have 6 of them, or some multiple of 6. So I've thrown in the 0 cells. Now what I do is I choose an arbitrary, I can't remember which I did, but I choose an arbitrary pair of 0 cells at random, and I drawing an edge between the two cells. And then I say the action on the cells actually induces an action on that edge. That edge will get moved to pairs of, so, and I'll put in 6 copies of whenever I add an edge, I'll have to add 6 copies. So if I add in one edge, the brown edge, the 6 copies are shown in brown. And I say, well, that's no good because if you just look at the brown graph, it's not path connected. I want my space to be connected, to be contractible. It has to be connected at least. The brown graph isn't connected, so I say, okay, let's go back, choose another edge at random, throw it in, and the orbit, and keep going until you're convinced that your graph is connected. But then there's a question, how would you show that the graph is connected? Well, we used yesterday's lecture. We build a admissible discrete vector field on the graph. I showed how that works, and you can do it quite quickly. So there's an admissible discrete vector field. These are arrows going from a n-1 dimensional cell to an n-dimensional cell. It's admissible, you can check. And then I say, okay, so that space there that I've built is homotopy equivalent to a space whose cells correspond to the critical cells here. Well, the thing about this is that every 0 cell, most of the 0 cells are involved as the source of an arrow. In fact, there's only one 0 cell which isn't labeled as the source of an arrow. So that space is homotopy equivalent to a space with one 0 cell. Well, it must be connected, path connected. Okay, so having done that, you now choose an arbitrary loop in your graph, maybe this one, and you say, let's just fill it. Fill the loop. Make it, and then add in a 2 cell. But you have to add in a copy of the 2 cell for every element of G, because G has to act freely. So you're going to have to add in 6, preserving the action. And it turns out that adding this one in is not enough. Okay. You keep adding in 2 cells and the orbit of the 2 cell until your space has trivial fundamental group. But how do you check if the space has trivial fundamental group? Well, it would be enough to check that the space is homotopy equivalent to a space with no 1 cells. Because if there are no 1 cells, fundamental group must be trivial. Well, so you build a discrete vector field, and here's one in which every edge is involved in an arrow. So there are no critical 1-dimensional edges, so the fundamental group must be trivial. And then it gets harder to picture, but you pick an arbitrary bubble in your space, you fill it with a 3-dimensional ball, and add in the orbit of the ball, and then you construct a discrete vector field to make sure that pi 2, the second homotopy group, is trivial. And then you just go like that. So in this case, you have to add in 4 balls. There is a periodic resolution for S3. I don't hit it doing this, but still. And that's implemented in GAP in the following sense. At least the cellular chain complex of X is there, has a free ZG resolution. And if you want to access it, all you have to do is give it your finite group, say up to what dimensions you want to calculate, so 6, we'll stop at 6, and you say R equals resolution, and then this is, well, we're going to do something that uses no information about the group other than it's finite, so it's not very sophisticated, but it builds a resolution, and it actually builds this number of cells, and in fact there's a nice pattern there, so it finds a nice number of cells. If you look at that, you can make sense out of those numbers. It's not so practical. I think it works for the symmetric groups S7, but then by the time you get to S8, S9, the number crunching just on my small laptop chokes. But still, you can build resolutions for some groups. But for some groups, you get quite far because I won't say too much about this slide, other than whenever you have a finite group and you want to calculate the homology of the finite group, It's known that the homology of a finite group is finite. This is a finite abelian group. So you can say, let's just look at the p component of that group, first of all. If we calculate it for each prime, the primes will only have to, you only have to run through the primes dividing the order of the group. And it's known that if you take the zero subgroup, p subgroup, for that group G, then there's a surjection. So if you could calculate this homology, you're getting close. You know that what you really want, the p part, is a quotient. And then there's a formula which goes back to Cartan-Eilenberg, which tells you what elements lie in the kernel. To get those elements, you actually have to do some kind of operating on the cohomology group. So you really need your arrows. You can't do it without the arrows, but if you have the arrows, you can work out those elements. And so you can do, for example, that runs on the laptop. You can get certainly up to the 4th degree for the Matthew group M24 just by simple number crunching and a few arrows. The 5th one on my laptop is just about out of bounds. I can say I got some bounds on what A and B are, but I can't say exactly what they are. I need a bigger computer or a better method. So that's discrete vector fields. So the double coset formula, what you actually do is you take for each double coset representative G. Okay? Oh, sorry, you're looking at the subgroup of P in G. P is the CeLO P subgroup of G. So you look at, in fact, you don't have to go through all double coset representatives, but you find a subset of double coset representatives, G, and then what you do is you take your Z, and P is the ZeLO subgroup, and then you conjugate P by G, which way to do it, I usually do it on the conjugate, and then you ask about the intersection. It might intersect. And the intersection embeds into P, but there's also another map here, which is given by conjugation. You can also get from here to here by conjugation. You get two maps. So what you do is you go to homology, and you say, well, here, you better make sure that the image of these two maps for each generator is equal. So you have to kill it, and then that's the kernel. Usually people talk about cohomology and they talk about the stable element method. I can't get my head around cohomology. I have to do things the normal way around homology, but it's the same. It's the stable element method. You'd find it in any of the books on cohomology groups. Ken Brown's book, for example. So there is an issue now then. So I'm at the stage where I take a group, and I've cheated so far because I've only taken groups that are either very small or act freely on a contractible space. But suppose you have a group like the alternated group A4, acts on this polytope, but it doesn't act freely. But all of the cells have stabilizer groups which are proper subgroups. So let's imagine then that we have some polytope with G acting on it. Take the cellular chain complex, and so you get a ZG resolution of the integers in which the modules are not free. Now, if you're at that situation, imagine then that somehow, and I'll say how in a moment, for each of these modules in this non-free resolution, suppose that you could work out some free ZG resolution for each of the modules from somewhere. Bearing in mind that the stabilizers are probably much smaller groups than the group G itself. Then there's a very old result of C.T.C. Wall, not stated in this generality. He was looking at extensions or even central extensions of groups, but the technique goes through in this generality. You can actually build a free ZG resolution from all of these resolutions and that resolution, these are free, that's non-free, in which the nth term is just a direct sum of the d's with p plus q equal to n. So if I just flick through some slides to indicate roughly how that goes, what I want to get across is where I'm using the arrows. Okay, so if you want to do this on a computer, you've got your polytope, and you've got this chain complex of the polytope, and G acts on it, so you've got that chain complex, and from somewhere, which I have yet to explain, you've got all of these resolutions, and so I'm going to stick them there, and any vertical map I'm going to call D0, and these are resolutions, so we certainly get D0 squared is 0 map. Now, these are all free, so by standard arguments, you can take a generator here, map it down, move it along, lift it up, and then induce the map across. You can induce a chain map between each of these columns. So you end up with a picture like that. Now, if that were a bicomplex, you'd be done. You'd say, well, just take the total complex of the bicomplex, and that'll do for our resolution. But the trouble is, so if it were a bicomplex, you'd just take the total complex with that differential, you'd be done. But the trouble is, when we lift it here, and I should have said, how do I lift? I use the contracting homotopy coming from the arrows whenever I lift. I'm not doing it in any functorial, I'm not doing it in any canonical way, so there's absolutely no reason why D1 should square to 0. So since D1 doesn't square to 0, I don't have a bicomplex. But D1 does square to 0 down here. So when I square to 0 here, I end up with something which maps to 0 there, so I can lift it. So if I take an element here, take D1 to there, I can lift it to here, and I can correct my non-zeroness by introducing a map going in this direction, everywhere. That can be done on the computer. All of the lifts are using the arrows. And then you say, well, okay, we'll try that for the differential. And then you ask, does that square to 0? And you find, unfortunately, what I really meant to say there was delta squared doesn't come to 0. That's a typo. So you have to apply the same trick again, correct by adding in more correction terms. And the result is that your resolution is built, but the differential is an infinite sum of components. But on any summand in the resolution, only finitely many terms in this infinite sum are going to be needed. So on any portion, you can actually calculate on the computer using these arrows. Said that. And then you may want to do things recursively. So the next bit is also important. Building a resolution is fine, but we'd actually like a contracting homotopy on the resolution if I want to use it again recursively. And there's a formula, which you can write down, which constructs a contracting homotopy on this resolution in terms of a contracting homotopy on C and a contracting homotopy on these resolutions, the virtual resolutions. So again, when you have your polytope, and you say my polytope is contractible, really you should go away and throw in the arrows to say how does it contract, because then you can, with a contracting homotopy on this and on that, you can build one on that, and then you can do things recursively. So if we can compute a free resolution, let's just suppose then that for one of these, so EK lambda is one of my k-dimensional cells in this polytope, and G EK lambda is the stabilizer group in G for that cell. And let's just imagine that from somewhere we could calculate a cell stabilizer. For example, my clumsy method, which I illustrated on S3. Then from that, it's not difficult to see that you can actually, this module here can be got from such a resolution just by extending scalars. So that's kind of an automatic thing that can be done on the computer. So if you can calculate free resolutions for the stabilizer subgroups, you can do Wall's trick and you get a resolution for G. So nilpotent groups are no problem, because you can work inductively, just like Heiko was doing this morning, down the lower central series. If you have an nilpotent group, you can work inductively. You can say, well, okay, could I find a resolution for the quotient? Maybe take A to be the center or something. Could I find a resolution for A? Okay, so find a resolution for the quotient. The quotient is a free ZQ resolution. Every cell will have a stabilizer, which is the group A. So can you find a free resolution for A, which in this case would be an abelian group? You can do that. And so you construct, using Wall's technique, a resolution for G in terms of those two resolutions. And I just flick through the next slide. Abelian groups, you can write down resolutions theoretically. So let me just, there's nothing much to say. I just flick through that slide. It's standard to write down a free resolution for an abelian group. And using that technique, you can work out, providing your computer is big enough, cohomology for crystallographic groups. They don't have to act freely because you do know in that case that the stabilizers of any cell will be finite. Arbitrary coxeter groups, infinite, finite, work in this way because you can build something called a coxeter complex, and every stabilizer is itself a coxeter group, so you can work recursively, and various arithmetic groups. So just to give an idea of some of the computations that you can achieve using this, the Matthew group M23, this is a result of James Milgram. On my laptop, it goes up as far as degree 6. You can get the degree 6 cohomology to be equal to Z17. And in fact, the Matthew groups are interesting. The Matthew group M23 is interesting in that it's the first and only real example of a group, a non-trivial finite group, which has 0 integral homology in degrees 1, 2, and 3. A direct product of 2 Matthew groups would also have that, but it's, apart from tricks like that, it's the only known group. And there's some suspicion that J4 might be another example of such a group. And for this reason, I'd love, and other people would love, to get their hands on the third homology of J4. Just at the moment, slightly out of reach, but nilpotent groups, so finite or infinite. So I took here a free group on 3 generators. You can do this in GAP. I used the nilpotent quotient algorithm that we heard about this morning, and I took a nilpotent quotient of class 4, is it, or whatever? I don't even know whether that's class 3 or class 4. Class 3 probably. And then you can just ask for the homology using this trick because it's nilpotent. You're done. And then you can also play with some arithmetic groups. And I have 11 minutes, so I'm going to do my best to say something about this calculation here. Okay, so I'm interested then in SL4 or PSL4 or GL4Z. So I look at positive, definite, real symmetric matrices. And I look at the space of all such matrices, and the space of all such matrices is a contractible space. It's cone. But it's a bit like saying the plane is a cone. That's the plane is contractible. There is the question: how would you put the cell structure? Because the contractible space on its own is not good enough. I have to put a cell structure, and this is where things get more difficult. So the next part of the slide is about how you put the cell structure. The answer goes back to Voronoi. So if I have a symmetric matrix, I can think of it as a quadratic form. There's an example. And given a quadratic form, I'm going to talk of the minimum lowercase m, min, just to be the minimum value attained by the form as I range over all integer vectors. So the min of Q, lowercase m, is the minimum value. And then capital M, the min of Q, is the collection of all vectors where the minimum is attained. So in this case, the minimum is attained, it's 1, and it's attained on the vector, I think, 1, 0, and minus 1, 0, give me x squared plus xy plus y squared equal to 1. I can also do 0, 1, and I can do 0, minus 1, and I think I can also do 1, minus 1, isn't it? So I get 6 vectors in that case. So that's just any vector I can think of as a quadratic form in that way. And let me say what I mean by a perfect form. So a form is perfect, a form Q is perfect if the following is true. It's perfect if whenever you give me a form P such that for all of the vectors V in min Q, the value of P equals the minimum of Q, that implies P is equal to Q. So if Q has that property, it's said to be perfect. There's another word I need. Q is well-rounded if the span of these vectors is equal to n. In this case, n is equal to 2. So of the forms, some are perfect, some are well-rounded. Going a little fast, but still it's okay. So here's an old theorem of Voronoi. There are only finitely many perfect forms up to SLNZ equivalence. So there's only finitely many orbits. And these cells, which are kind of convex holes or whatever, tessellate the cone. So if you can find the perfect forms, you kind of have a tessellation by Voronoi. Now that's simplifying things. There's a lot of computing and work to be done in that. There were 6 here, so you kind of get a hexagon. You get kind of like a hexagonal tessellation, but the dual to a hexagonal tessellation is a well, you get a hexagon is a triangulation. Yeah, in n variables. But now I've jumped, in n variables. Yeah. But now the pictures will only be for 2. Yeah. So this is the tessellation that you get from this. So you've got cells here, that's the fundamental domain. But it's not a CW structure, because CW structures, the cells have to be homeomorphic. I mean, they have to be homeomorphic to this isn't compact. This is non-compact, that cell. It goes off to infinity. But we can get around that problem by just adding in the points at infinity, cusps. And so what you get then is you can get a tessellation of the plane, and you add in points at infinity, but you can actually do better, because all I want is a contractible space on which the group acts. So you can get a smaller space. I think it's due to Ash, or maybe Soule, or I'm a bit nervous about who I'm attributing this to. But there's a homotopy retract. So this is the, I should say this is the upper half plane. And this thing in red is a homotopy retract cubic tree. And so this group SLN or whatever, or SL2, acts on this cubic tree as well, this retract. So there you have it. You have a cubic tree. It's a tree is contractible. SL acts on it. And okay, it doesn't act freely. You've got stabilizers. But the stabilizers are finite. So you can stick all of that together and use Wall's technique to get a resolution for SL2Z. Well, okay, I've illustrated there for SL3Z. So this is a gap command. So this is where I'm cheating a bit. The first line here, I'm not really able to compute this at the moment. I ask a colleague, a co-worker, Mathieu Detour, who's very good at writing things in C++, and he gives me the upper half plane, the cell structures, with the stabilizer groups. And so I just stored them in a database. And then this command here implements Wall's resolution. So you get a resolution, and then you say, what's the homology or whatever you want to do with it, and you get that. And then a discrete vector field on the space of the cone, or the cubic tree, or Ashes retract, would actually allow you to construct a contracting homotopy on R, which would be very useful for constructing things like Hecker operators that are of interest to number theorists. But at the moment, I certainly know how to construct a contracting vector tree on the cubic tree. That's implemented in GAP. But for these higher dimensional cellular complexes for arithmetic groups, at the moment we don't actually have a formula or the understanding of how best to implement the contracting vector field or the discrete vector field. But I think, sorry? I did, yes. So yesterday, though, it's yeah, I mean, arrows. So I think I'll stop there. So if you're interested, you can look at there are 2 more slides. I won't read through them. But what the next 2 slides do, I'll just tell you quickly. I'm not going to do. What they do is they say, well, SL2 acts on the cubic tree. So what does, maybe this answers your question, what do I mean by a discrete vector field in this case? Well, the tree has, let me go too quickly here. This is the tree in blue. Let me go even faster. The group acts on this tree, so really no, it's not free. It's not free. That's right. It's not a free action. Yeah. That's right. It's but on this yeah, it's not a free. Yeah. Okay, no, but it's just. Yeah. So each cell has a stabilizer. Is all that really means. Every cell has a stabilizer subgroup. So yeah, you have to keep a record of that stabilizer subgroup. That's part of Wall's lemma or proposition. But what I want to do now is actually just tell myself, how do I construct this tree? So each thing here is a kind of a coset, each vertex, but I'm going to think of it roughly as represented by an element of SL2. Let me think. The T's here kind of correspond to the edges, and the S's correspond to rotating around it. And so what a discrete vector field corresponds to in this case is just a way of expressing an arbitrary matrix in SL2Z as a product of these two. And you can do that. So because this is one-dimensional, the notion of a discrete vector field is just this is an amalgamated product, yeah. But I'm not really I'm just using the fact really that this is a CW space of any dimension. In this case, it's dimension 1, so you get an amalgamated product. Yep, and the explanation I won't go through, but that's as an exercise. Then, can you express A as a product of S and T? I won't click on. It's on the slides if anybody's interested in how to do it. But what that amounts to is building or designing a discrete vector field. And I stop there.